All right, so welcome back, everyone. So today is our last seminar for the academic year, and it's our pleasure to have Karan Srivastava. So he'll be continuing actually the lecture series that we started at the beginning of the year on machine learning for discovery for scientific discovery, and today he'll be talking about computational algebraic methods for abductively inferring axioms to explain a phenomenon. Yeah, thank you, Karan. Yeah.
Thank you for the introduction. And thank you all for having me. The pleasure is mine. So yeah, today I will be talking to you about this problem of abductively inferring axioms when you have a background theory or an axiom system that can't quite explain a phenomenon that you think is true. So my name's Karan Srivastava. I'm a fifth going into sixth year PhD student at UW-Madison, and this is work I did with my wonderful collaborators listed here over the course of the last year while I've been an intern at IBM. The core sort of motivation for this entire series of scientific discovery has been to look at this what we know to be the scientific method and sort of ask how can we utilize modern tooling, modern technology to sort of augment different parts of this process. We've seen a couple over the last few iterations of this talk with Christina and Ryan and Sanjeev and Lior. Um, to give you a quick high-level summary and overview, the first step of the scientific process is that we start with some known theory, and of course, we want to observe some phenomena that we can't explain. Technology, of course, it's no surprise, has been immensely helpful in this. The reason we are able to do most of the science is because we've developed lots of hardware and engineering that have developed tools that allow us to extend our observational capacity and gather lots of data. Some examples are the Hubble telescope, which generates hundreds of gigabytes of data per month, and future iterations of even more advanced versions of telescopes that have been created since, or the Large Hadron Collider. So, observing phenomena and technology has been immensely helpful in scientific progress. The next thing we typically do is generate hypotheses based on either the data we've gathered or the axioms that we know to be true or we assume to be true, and the heuristics that we explore there. So, how technology can be used, or machine learning or AI can be used in this space, is precisely the topic of this sort of scientific discovery with Gen AI, statistical and symbolic methods that my collaborators and their peers have talked about in this seminar. To give you a quick overview of what methods like this look like, we all know and love the traditional process of generating hypotheses, where we study theory that is known, and we look at all the heuristics we have, and we try to come up with hypotheses and test those hypotheses on data. Of course, coming up with new theories manually is challenging, and we've seen evidence over the last few talks about uh, how this is sort of increasingly becoming a bottleneck for discovery in science today. So, how does technology help? Well, there are different classes of methods. Some methods are purely data driven. The example I'm giving here is this paper called AI Feynman, which I believe Christina mentioned in her talk. So the idea for AI Feynman is that when you have a very large data set, you can train a neural network on this data set to become a kind of oracle, which you can then probe to find symmetries, translations, to find hidden structure in your data and use that to reduce your data set to something smaller, and at each iteration try a brute force or polynomial fit. And this works really well with large data sets. It also works really well because you don't need any domain knowledge to run this. You just need data. The second approach is to look at both data and background theory. This was the talk that Christina gave in the seminar. where we looked at this tool called AI Descartes. The idea there was to gather a bunch of data, and then use a traditional symbolic regression approach to fit different formulae to that data. But then, in order to verify which of these formulae work or do not work, we test those formulae on background theory by using an automated theorem prover to see if we can derive those formulae from background theory. The advantage of this is that it can work with really small data sets, and when your theory is sufficient, you recover a certificate of derivability from your hypotheses. So over here, it's sort of different to the previous paradigm where we're generating hypotheses based on data and axioms, and we're sort of testing it on theory. The last method that I'll go over very quickly is the previous iteration of this talk, AI Hilbert, which was done by my collaborator Ryan Corey Wright and his collaborators, some of whom helped with this work as well. So the idea here is that instead of treating training and testing as two different steps, we can sort of merge them and both fit the data as well as fit the background theory in a single step. The advantage of this kind of approach, which was implemented using polynomial optimization, is that you can generate certificates of derivability while doing your search. And when you solve this polynomial optimization, your solutions are provably optimal in this sense. I'll go over this method in a little more detail because it's going to be relevant to what we're doing. But in overall, the idea is for most of the scientific method, we've seen a lot of progress in the use of modern tooling. And we've gotten a lot of mileage out of technology. But one of the things that we haven't talked about is in all of these steps, we know that there are often cases where the theory that we're starting with, the sort of core assumptions of physics that we're working with, they might not be correct. And so oftentimes in physics, we have, or in science in general, we have to revisit our assumptions. With data-driven approaches, the typical issue is that you can generate formulae that are either difficult to interpret or not consistent with theory. And with the approaches like AI Descartes and AI Hilbert, we've seen that we do get certificates of derivability when your theory is complete, but oftentimes that's not the case. To sort of throw out two examples in cosmology, you have this problem of lithium abundance where we have sort of many different competing models of cosmology, but and most of them do a very good job of explaining exactly how much hydrogen and helium we end up observing in the universe. But to the best of my knowledge, that this problem of lithium abundance, of why we're seeing more lithium than our models predict, is still an open question. A sort of historical example, going from Newton to Einstein, which was, I think, the classic example of when we needed to update our theory, was this problem of the perihelion precession of Mercury. Mercury's orbit was predicted by Newton to be perfectly elliptical. And even if you take into account the effect of gravity by all the other planets on Mercury, the orbit undergoes a sort of precession. And so Newton predicted that this precession was, I think, on the order of 531 arcseconds per century, which turned out to be incorrect. And he was off by about 43. It turned out that the radial equation that he was using needed a few modifications, which Einstein had proposed in his first relativity paper. And so in both these instances, you're seeing either an exact example of or a need to update theory that we have. So to summarize, data-driven methods can be limitations with data-driven methods is that the hypothesis we get may fail to be consistent with theory. With both data and background theory and unified methods, we see that to really get axioms of to get derivability certificates, we need our axiom systems to contain complete information. And so, in lieu of this, what we want to look at in our work is when our theory is inconsistent or incomplete, but we have phenomenon that we do want to explain. Is there an automated way to generate corrections to this theory? And that's really what we're going to be looking at today. So, as I mentioned, I wanted Ryan gave a wonderful talk a few months ago on AI Hilbert, and I think it's a good starting point to understand how our system works. So where we're going to start is by looking at AI Hilbert, but rephrasing the scientific discovery problem that AI Hilbert solved as a problem in algebraic geometry or computational algebraic geometry. So, as I mentioned, the idea for AI Hilbert was to run a polynomial optimization that minimized the empirical error of your formula Q on some data set. That's the first term in this optimization objective. But we regularize that with how far Q is from being derivable from your background theory. So the second term you're seeing here is the distance between your proposed formula Q and some background set of axioms A. One thing to mention is that as Ryan mentioned in his talk, and as I will mention in this talk, we're going to be working with us in the situation where all of our axioms and all of our discovered phenomena can be encoded as polynomials over some basis. So by that, I mean polynomials that are over either traditional indeterminates or trig functions, exponents. We won't be dealing with partial differential equations or ODEs. So how does this work? Well, the core idea for AI Hilbert was that when we're working with just polynomials, we can reduce our search space greatly if we are trying to consider the space of derivable functions from some axiom theory. So let's say we start with some axioms A1 through AK. These are, again, polynomials. The core idea of AI Hilbert comes from this result called the positive Stalinsatz, Puttinar's positive Stalinsatz. The idea here is that if you have a polynomial Q that vanishes exactly on the solution set described by your axiom system, so the solutions in Rn to not just one axiom, but all of them, what the Stalinsatz says is that we have a closed form expression of all such polynomials Q. Specifically, Q can be written as an algebraic combination of your axioms. And so the core mileage we get out of this, or the key takeaway that Ryan and his collaborators used, is that we can express algebraic derivability from axioms as an algebraic combination of those axioms. To give you a concrete example, let's look at at Kepler's third law of planetary motion. So this is Kepler's third law in context of the two-body system. And we know that this can be derived from a list of 5 axioms. The first axiom is the equation for center of mass of the two bodies. The second axiom is the equation for gravitational force. The third axiom is centrifugal force. And the fourth axiom relates centrifugal and gravitational force for a two-body system, while the fifth relates the frequency and periods of motion. So we know that there's a algebraic derivation you can do go from these axioms to Q. But instead of doing this algebraic manipulation, what we note is that if you define a clever set of multipliers alpha 1 through alpha 5, again encoded as polynomials, you can write Q as an algebraic combination of these axioms with these multipliers. Note here, as I mentioned before, that I'm saying that we are using polynomials, but really, if you notice Q over here, the first version of it is an algebraic function, but we can clear denominators, square both sides, etc., etc. So we're capturing a little more than just traditional polynomials. But regardless, you can think of derivability in our context as algebraic combinations. Because of this, we can then define that distance that I mentioned earlier. What is the distance between a proposed formula Q and a set of axioms A? Well, we know Q can be described as some algebraic combination of those axioms. And so what we define this distance to be is just the minimum of the coefficient distance between Q and any polynomial in your any polynomial that's an algebraic combination of your axioms. So any polynomial that's derivable from your axioms. Given that, we can then state and solve this optimization problem that I mentioned before. The way they actually do it in the original paper is they set it up as a linear program, but the details there aren't too relevant for us. What is relevant is that this can sometimes be computationally expensive. Certainly in the best cases, like for Kepler and a few other problems that were reported on, the good uh, the benefit of this method is that the LPs can be solved pretty quickly. But of course, with the larger the system that you're trying to solve with this, the slower you get and more memory you require. So the example I'm giving here is for discovering the radiational gravitational wave equation from the original paper. This took about 650 gigs of memory and many hours on MIT supercloud infrastructure. So the first question that we wanted to ask was, can we speed this up? And this is where geometry starts helping us out. So we're going to essentially restate this discovery problem to a geometric problem. And then the machinery we build there will be helpful for us to solve this abductive inference problem that I mentioned at the start. The idea here for geometry is that you can convert this discovery problem to a projection question. Let's take this axiom that we know to be true, that centrifugal and gravitational forces are equal. So in some high dimensional space, this defines a plane. Well, if we're iterating our polynomial optimization over all possible formulae Q, Q can uh, Q can cover a large sort of set of surfaces. But the idea here is that if we know these axioms to be true, which we're assuming in the AI Hilbert context, we don't really care about the components of Q that are not on this plane, which we know to be a ground truth. What we really care about is the component of Q on that surface that represents the ground truth. In practice, each of your axioms defines a surface, and we're going to be taking the intersection of all of those surfaces. And we're going to be looking at the component of Q on that intersection. But the idea is still that we care about not just Q, but the projection of Q onto this surface described by our axiom system. So computational algebraic geometry comes in as a toolkit to help us try to make sense of this. The core piece of machinery that I'll be using for most of this talk is going to be a variety. So this is really translating everything we're saying about axiom systems to something more geometric. So whenever I say variety, I just mean the set of real solutions to your polynomial axiom system. You can also call it an algebraic variety, and it'll be denoted by this V of A1 through AK notation. So really what you should think of this as is just the solution set. And for now, we'll take this solution set and we'll do some projections to reduce the search space that we're looking at. The second piece of machinery comes from the Nullstellensatz that I mentioned before, where we saw that every polynomial that's derivable from your axiom systems can be written as an algebraic combination. And so what algebraic geometry gives us is the notion of an ideal, which is essentially just exactly this set. It's the set of all algebraic combinations of your axioms. That's what, and we'll say that that ideal is generated by the axioms. And so you should really think of this as a closed form representation of the space of all algebraic consequences of our axioms. It's the space of all phenomena that AI Hilbert will search over. So we've defined varieties and ideals, but how does this help with this projection problem that we've asked? Well, we have a couple of facts that are gonna come in handy. The first one is that if you have an algebraic consequence of your axioms and you append that to your axiom list, you're not really adding any solutions. And so the idea is if you have the variety that is generated by a finite list of axioms A1 through AK, it's the exact same as the variety generated by the infinite set of all algebraic combinations of A1 through AK. The second fact that we're going to use is that the same ideal or the same set of algebraic combinations can be generated from by different sets. This is very, very analogous to basis vectors from linear algebra, where you could have multiple different bases for the same space. In fact, this is, in a way, a generalization of that to polynomials. What this buys us is a very well-known theorem in commutative algebra called the elimination theorem, where just sort of analogous to a standard basis when you're doing some form of Gram-Schmidt algorithm for linear surfaces. We know that there exists a unique generating set, which we call a Grosvenor basis, which has this property that if I want the projection of the variety defined by my axioms onto some smaller ambient space, instead of defined over n variables, it's defined over the first r. The set is infinite, but we know that it is generated by the intersection of your Grosvenor basis, which you can compute for your variety or your ideal. The elements of those Grosvenor bases that lie in the ambient space that you care about exactly generate the projection of the variety. So what does this buy us? Well, if our theory is sufficient and complete, we can actually sidestep the AI Hilbert mechanism entirely, and we can just purely project the variety generated by your theory onto the variables that you care about and use that as your mechanism for generating hypotheses. If your theory is insufficient in that if you project down, you don't have enough information, and so your projection ends up being trivial. Or a different way to put it is if you're missing some essential axioms, then what you can do is still project to a reduced search space, and then along with data run AI Hilbert on that. And this was the first set of results that we saw, where we can achieve both a reduction in LP size and a massive increase in speed up. So the first set of columns you're seeing here is the original AI Hilbert paper and my runs of the original AI Hilbert code for various problems. The middle pair of columns that we're seeing is the results of when we do have complete theory, does projection work? And as predicted, it does. And the last set of columns is when we remove certain essential axioms from each theory, so that projection no longer works. If we still reduce to a smaller search space, we see that the number of monomials here you can really think of as the size of the LP being solved. We're seeing that we get a massive reduction in the size of the LP that we need to solve, which results in a pretty big speed up. Are there any questions so far? Please feel free to interrupt if there are. Okay, I'll keep going then. So with having developed this sort of language of varieties and ideals, now we're sort of ready to look at how we can abductively infer axioms if our systems are incomplete or incorrect. So to be concrete, so far we know that, let's say we can go from these axioms to Kepler's third law. We know that if you don't know how gravitational force works, then you can no longer derive Kepler from this new system. And so you need data and some external process, either AI Hilbert, AI Feynman, BISR, some data-driven approach to generating your consequence or your phenomenon. So the question is, can we go back with this new information, knowing that we can discover Kepler, knowing that this is a hypothesis we believe to be true, but we still can't explain, and infer what axioms we would have needed to add, in this case, the knowledge of what the gravitational force equation is, in order to then append that to our theory, to make our theory more robust. So let's make this concrete. We're given a polynomial, Q, which was going to represent our phenomenon. We're going to have an axiom system, A1 through AK minus 1. For now, we'll just assume we're missing one axiom and we'll generalize later. And we know that A1 through AK minus 1, the known axioms that we have, do not prove Q. So our aim is to generate a list of candidates, let's call it AK hat or AKI hat, so that if we append any one of these candidates to our axiom system, we can in fact prove Q. We need to make some constraints to make this problem both interesting and well-defined. We're not going to assume that we have any data for the missing axiom. If we did have data for it, it becomes equivalent to a hypothesis generation question, where we can do sort of traditional search methods. In fact, stronger than that, we're not even going to assume we know the exact variables over which AK is defined. Other than the fact that it is defined over some subset of variables of the entire system of Q along with the known axioms. In other words, we can't create variables out of nothing, which hopefully intuitively makes sense. The third thing we're going to assume, and I'll make this a little more precise in a moment, but we want to assume that AK is in some sense simpler than Q. This is to avoid the case that, well, we could just append Q to our axiom list and that sort of explains Q trivially. I'll make what I mean by simpler a little more precise in a few slides. And the last, as I mentioned, is going to be that we're going to generalize to multiple missing axioms or multiple incorrect axioms in a moment. But for now, we'll just stick to one for illustration. So how do we go about discovering this gravitational force equation? The key idea for our problem is going to be to study the reducibility that is introduced by Q to the system of known axioms. It's going to say something essentially about the residual of Q with respect to the known axioms. And I'll make all these words precise. So what do I mean by reducibility? Well, we've defined the notion of a variety, but we can define the notion of an irreducible variety somewhat naturally, which is a variety is irreducible if you can't write it as the union of two smaller varieties. I want to be careful here and note that all of these varieties are irreducible, including the third one, which it might not seem to be the case, since you have these two connected components. But irreducible does not necessarily mean connected, since we're also going to be working purely over real numbers. Of course, then we can define the notion of a reducible variety, which is that it's not irreducible. It can be written as the union of two smaller varieties. On the left, for example, your two smaller varieties could be the line x equals y and x equals negative y. And you can imagine something similar for each of these other examples here. So how does this help? Well, one thing to note is that two irreducible varieties can be intersected to obtain reducible varieties. So it's not necessarily true that irreducible varieties being intersected stay irreducible. We can introduce some reducibility by taking intersections. And so why this helps is, let's say we have A1 through AK minus 1. As I mentioned, for this talk, I'm just going to be, for now, I'm just going to be sticking to one missing axiom. Well, let's look at what happens when we take this intersection. between these two, the variety is generated by A1 through AK minus 1 and the variety generated by Q. Well, taking the intersection of these varieties is the same as just adding Q to the list of axioms to the polynomial system. When we add new polynomials, we just take intersections. And as noted before, there's no difference in taking the variety generated by the known axioms in Q and the variety generated by the ideal generated by the known axioms in Q. Well, why is this helpful? Well, we know that by assumption, Q is some algebraic combination of my known axioms and some unknown missing axiom. Since we don't know the missing axioms, we don't even know the algebraic multipliers that are required. Otherwise, we could just compute a residual. But we do know that as ideals, as sets of polynomials, the ideal generated by A1 through AK minus 1 and Q is the exact same as the ideal generated by the known axioms, and not the unknown axiom, but a multiple of the unknown axiom. And that's really the residual that we want to study. The reason this is important is because let's just go back to the geometric picture. We know that we have a variety defined by our known axioms. We know that we have a variety defined by Q. What we're saying through this is that the intersection of those two varieties is the same as the intersection of the varieties generated by the known axioms and this residual term. So the question really becomes, can we coax out this residual term given that we don't know any of these multipliers? The thing to note here is that this last variety that I mentioned, the variety generated by alpha k ak, that variety is reducible. It's not necessarily irreducible. Since you have two polynomials that are being multiplied together and set equal to 0, your two reducible components are, well, the first polynomial, the surface defined by the first polynomial, and the surface defined by the second polynomial. So as long as Q contains some non-trivial components in the known axioms, then we know that intersecting Q or introducing Q to the system introduces some reducibility that's directly related to AK and alpha K. When I say it contains some non-trivial components, what I really mean is that alpha K is not just 1, because then AK would have to be Q. So this is going to be our aim. Given the known axioms and some phenomena, we want to study the irreducible components of this combined variety. And really the motivation is going to be to remove the components of Q that are in the directions, quote unquote, or that are correlated to A1 through AK minus 1. Usually a good analogy for this is PCA, where when we have some data set for which we're trying to find principal components, we're really trying to look for components that are in some sense orthogonal to each other. And that's really what we're doing. So earlier when I mentioned that AK needs to be simpler than Q, I mean simpler in this sense, where the axiom that you're trying to add should explain Q in a way that is minimal with respect to the residuals when we take Q in some sense modulo to A1 through AK minus 1. So what are the concerns that we need to address here? Well, first off, if I have some intersection that I want to study, well, there could be infinitely many ways to come up with pairs of polynomials or groups of polynomials that intersect down to that surface. Here you can see an example here of if you take a sort of tilted circle, here are two completely different surfaces that intersect to give you this circle. Well, we have this is where some algebraic geometry machinery really comes in handy. We know that every ideal, at least in our polynomial ring over R, is going to have a finite set of generators. In other words, even though there are other surfaces that could intersect to give you your solution space, that intersection is in some sense unique. There's only a finite set of generators that you need to consider of that intersection. The second concern is that, well, we're talking about irreducible components, but we want to have a computational way of looking at a complicated surface and breaking it up into into its irreducible components. This is really the key theorem that is going to drive all of our that's going to drive the system, which is the primary decomposition theorem, which put geometrically, it says that every variety can be written as the union of irreducible varieties, and we have computational methods of generating this. The detail I'm skipping over here is that every irreducible variety corresponds to a very particular kind of ideal called a prime ideal. Um, we don't need to get into the weeds of what that is, but really when we're doing this decomposition, we're going to be doing it at the ideal level. And we'll see some particular examples of that. So here's what we're going to do. We're going to take our theory and we're going to take this hypothesis that we have for that explains some phenomenon. The first thing we're going to do is define the intersectional variety between between the known axioms and Q. The next thing we're going to do is use some computer algebra tools to compute the primary decompositions of this, decompose it into its irreducible components. We know that one of these irreducible components exactly explains Q in a simpler way, or another way to put it is our missing axiom is in one of these irreducible components. So what we'll do is we'll, through our Grosvenor-based method earlier, we'll look at the generators of each of these irreducible components, and we'll just manually test it using that exact same projection idea that I mentioned before to see if the new surface defined by A1 through AK minus 1, the known axioms, and this candidate axiom proves Q. If it does, great. And then if it doesn't, we reject it and we move on to the next generator of the component. At the end, hopefully we have a list of candidate axioms that explains this phenomenon that we're trying to, that we have. So let's actually look at how this performs on some problems. Since we had this example before, let's see what we get here. We have Kepler's third law, and we have these four axioms over here. I removed the center of mass axiom since it's not quite essential. So these four axioms are sufficient for our purposes. And let's say we get rid of any knowledge about what the force of gravity actually is. But we know that from AI Feynman, AI Hilbert, ISR, we know that we have all of these systems that if given data, regardless of the axiom that we never knew, we can still derive Kepler's law. So what do we get from this primary decomposition? Well, we get, as I mentioned, two varieties, two irreducible components. And the generators of the irreducible components is what you're seeing here. So when we go through the generators one by one and we do this sort of projection derivation, we're going to see that we actually do see the gravitational force equation. And in fact, out of all the generators of these surfaces, this is the only one that can explain Kepler's third law. Okay, let's do a different example. What if we're missing the relationship between frequency and period? So we didn't know that. Well, the primary decomposition here gives us 5 irreducible components, but really the relevant ones are these last two components. So each of these components, again, define two separate varieties. And when you take the union of those varieties and the varieties generated by the original components, you get the variety defined by the known axioms in Q. You may have spotted it already, but there are polynomials here that our system will flag as appropriate candidates since you can derive Q. Well, there's two interesting things going on here. Well, we know WP minus 1 is true. Why are we saying WP plus 1? This is an artifact of that multiplier that I mentioned earlier in the residual terms, where the thing that you're essentially analyzing at the end is not just the variety generated by your unknown axiom, but the variety generated by the unknown axiom and its corresponding multiplier in the derivation. And so it just turned out in this case that alpha 4, the multiplier for WP minus 1 was WP plus 1. This is interesting because on the one hand, we're seeing a sort of alternate universe in which WP, the relationship between frequency and period, were that P is negative 1 over W. It turns out, at least in context of Kepler, you're still consistent. But of course, you can use known inequalities to sort of see through and vet that out. The second thing we're seeing is this odd looking axiom candidate, but I argue that it turns out that it's not that odd. The reason this is showing up is because it's the exact same axiom as my centrifugal force axiom, this A2, but we're just swapping W equals 1 over P into it and clearing denominators. So we're not really gaining any new information. I think we're also swapping FC equals FG from axiom 3. Another problem, we looked at this for a host of different problems. The other one I want to highlight is this problem from the original AI Descartes paper of Einstein's relativistic time dilation law. The idea is that we want to figure out the relationship between the speed of light in different contexts, where the two situations we have here is you have a stationary mirror and a stationary light clock and a moving light clock. And we know at this point that the speed of light is constant. But the thing that the original authors in AI Descartes were interested in was that can we derive this time dilation law on the right from the axioms from this experiment observed on the left? The context in which they looked at this problem was that what if we had a system of incorrect axioms? So the two axiom systems you're seeing here are exactly the same aside from the second one, where the second one assumes a Newtonian version of the velocity of light in motion. So in both AI Descartes and AI Hilbert, we saw that regardless of whether you're working with the correct or incorrect theory, you can derive the time dilation law exactly with data, of course. And in addition to that, you can select which between the two of these are the correct system. You can select which one is the correct axiom. Even if the system is incomplete, you can run AI Hilbert or AI Descartes to still generate the correct hypotheses. But the tricky thing that you're going to run into there is that AI Descartes, while it will discover the correct formula, it'll struggle to verify it since your axiom system is not complete. Whereas AI Hilbert will also find the right formula, but it won't give you an exact certificate of derivability because this phenomenon, in fact, is not derivable from your remaining axioms. So what happens when you have no knowledge of the speed of light from a moving light clock? Well, what our system detects if you give it the remaining axioms is that it proposes both of these two candidate axioms. The first one is exactly the missing axiom, and the second one is again as the missing axiom replaced in axiom 5, where f is equal to 1 over dt. We're just saying that cdt is equal to 2l and clearing denominators again. Again, we're getting the same information from both axioms. So we tested this for quite a few different problems, most of which were from the original AI Descartes and Hilbert papers. We tested it for a more recent work from 2019 on the carrier resolved photo Hall effect that was published by Oki Ganawan from IBM in Nature. And we found that in most examples, we can almost always, if not always, recover axioms that were missing. The only cases in which we cannot recover axioms that are missing are when the axioms involve new variables that, as I said earlier, we can't generate variables from nothing, unfortunately. So this is all in the case of if I just don't know one equation? What if I'm missing multiple axioms? Well, and again, you're either missing multiple axioms or you need to make more than one correction to your theory. Well, if I do this primary decomposition, and if we start studying the generators of each of the irreducible components, we're going to see very quickly that we don't recover WB minus 1 or FC equals FG. So this begs the question, since we don't seem to recover the two missing axioms, what exactly are the criterion for derivability? We have a theoretical which talks about the relationship between the dimensions of ideals and when the corresponding varieties share irreducible components. The idea is, let's say we're missing R axioms, or we need to make R corrections, and we are trying to explain J phenomena. Um, then the idea is that we can recover the sort of missing R plus 1 through K axioms from some shared irreducible component, only if the dimensions of the ideals or their corresponding varieties line up. I haven't said much about dimension, but the main idea is that when you just take a variety and you add an equation to it, we're taking the intersection of that variety with your new polynomial surface, as mentioned before. Um, all we're doing with this dimensionality analysis is looking at when are we reducing the dimension versus when are we staying the same. Because taking these intersections turns out only decreases the dimension by at most one, not one every single time. So what this is saying is, to guarantee recovery, if you lose some number of dimensions in your missing axioms, you need to make up exactly that many dimensions from the phenomena that you are adding back in. This is kind of in line with what we said before, where if let's say we had two phenomena that we are trying to explain, then it all boils down to the fact that these ideals only reduce nicely in terms of these irreducible components, alpha k minus 1, a k minus 1, and so on, when the dimensions sort of line up well and when you're adding back enough information. So what's happening here is that we're losing, to speak a little bit loosely, we're losing two dimensions of information. But when we add q back, or we take this intersection, we're only gaining one dimension of information back. But we are still gaining one dimension of information. So let's go back to that primary decomposition and see what we're recovering. I'm not listing the entire decomposition, but this is the essential component in that primary decomposition. If you run the second half of our system, which is the check for derivability, it's gonna come up with a candidate in this component that does explain Q. So what's going on here? Well, compare what we found to axiom 2, the centrifugal force axiom. What we're seeing here is we've essentially just discovered a reformulation of centrifugal force, but with Fc equals Fg swapped in, and with W equals 1 over P swapped in. So essentially, we're getting a coupled version of these two axioms. Now, of course, if you want to decouple it, you would need to feed in more phenomena into the system, one more phenomenon that contains a dimension of independent information. But the idea is still that we're still gaining something when we do this method. Let's take it one step further. What if we're missing three axioms? Now, this kind of seems ridiculous that I have one axiom and one conclusion. That conclusion does not follow from the axiom. In this case, you would say, okay, great, just append Q to the axiom list because we have no information. Well, let's look at one of the components in the primary decomposition here. What we see is that same axiom that we inferred in the previous case, centrifugal force with the Fc equals Fg and Wp equals 1 substituted in. The interesting thing here is that in the previous case, you could have made the argument that, well, we know centrifugal force exists. We're just plugging things into that equation. But over here, we're really generating this centrifugal force axiom from scratch without any knowledge of it. And so even though when you're missing more and more axioms, of course, the doing this kind of approach gets more challenging. We can still get some mileage out of it, even if we can't decouple all the missing axioms that we lose. So we tread this out for all possible pairs of axioms and triples of axioms. And as we see, you can't always recover even a coupled version of the missing axioms. And of course, if you look at the cases where we're missing two axioms, we have a lot more success than when we're missing three axioms. Granted, it is a four axiom system. And so this is still we can still recover some information in most of these cases, which I think is still interesting. I should also note that this method runs pretty quickly for most of the systems we test. The CPU time here is just a laptop on a standard MacBook laptop. So time complexity for now isn't too much of a bottleneck. We also did the same thing with all the problems from Einstein's time dilation law that I mentioned earlier. We took all pairs of axioms, or triples of axioms, and we see very similar results where when we're missing more and more information, it gets harder to recover. Um, the interesting row here, I think, is row 4, where if we don't know CDT 0 is equal to 2D, CDT is equal to 2L, both of these are statements about how long light takes in both the stationary and in the motion case to bounce from one side back. So we can recover essentially a coupled version of these axioms where we start off not knowing anything about the speed of light, but we can still make inferences, which I think is pretty cool. So we tested this out for a few other problems, and we see kind of similar success rates as what we just saw for Kepler, for Einstein's time dilation, for the neutrino decay equation, and so on and so forth. What we see is some success, and really most of the success cases here are when we're missing 2 or 3 axioms. The more axioms you're missing, of course, the harder it is to recover even coupled versions of that information. But yeah, that being said, I'll wrap up with some limitations, ongoing work, future work, and so on and so forth. The first one is, of course, that we're restricting in our system to only work over polynomials. Granted, we're allowing for polynomials over different bases, like trig polynomials, but we still cannot handle ODEs and PDEs just yet. The second big one, which for the sake of time, I didn't really get into too much, is that this method is sort of a bit sensitive to noise. Because all of the steps that we're doing are computer algebra steps where we're computing Grosvenor bases, computing primary decompositions, these methods are known to be a little bit sensitive. They're known to be somewhat sensitive to the noise and the coefficients of your polynomials. There are certain kinds of noise that you can capture, and certain kinds of noise that become a bit harder. But overall, this is also the second sort of, I believe it's the second bottleneck that we need to solve in order to make these systems truly applicable. But given that there's more work to be done, I still think, and we still believe that this is a step in the right direction, where we really should look at every aspect of this scientific process. And I think it's a good exercise to look at how we can augment each of these parts with modern tooling, modern math, AI. And I think overall, this is a step in the right direction, which hopefully will lead to some awesome new science. But that being said, that was the talk. Thank you very much for listening and having me. I'm open to questions.
Yeah, thank you very much. Any questions or comments?
One quick one, Karen. I work with Karen
Yes.
a bit, but This is John Lenchner. Is there any ability to work with inequalities? So, for example, you have the positivity of masses and the uncertainty principle. They're all, and there are other examples.
Yeah, that's a great question. So not currently. We didn't, given the problems that we were looking at, we didn't run into the problem of inequalities too often, so we didn't think about it too seriously. There is some literature on semi-algebraic sets and doing reductions in these semi-algebraic contexts, but what I don't believe exists for now is a notion of doing this primary decomposition in those contexts. So we wouldn't be able to handle inequalities, which is why when we were looking at this WP minus one, WP plus one example from earlier, it really, our system would generate these candidates, but then it would take some human heuristics to sieve through these candidates and say, okay, we have some inequality knowledge about W and P, and so we can throw that candidate out.
Yeah, so it seems like you could deal with it as post hoc constraints on anything
Yes.
that's generated, right? Okay.
So in
Yeah.
Yeah, I
correct,
asked.
so if I can add a comment, this is Sanjeev Dash from IBM, one of the co-authors. So yes, indeed, so WP plus one could be ruled out knowing that W and P should be both positive terms. But in general, you're correct that it's more complex dealing with non-negativity. So in particular, if you have polynomial equations and inequalities and you want to do a forward inference, as in implications, you have to start getting into the polynomial optimization and other things and not just Grosvenor basis type systems. And definitely the reverse is a lot harder. I do not know if it's even well defined. So to say that if I have a system of polynomial equations and inequalities and I have a particular consequence and I want to go backwards from the consequence, and the consequence could be an inequality. So I say, okay, what is a missing inequality or equation I should look for? That's definitely harder. It can, I believe, one can do something there, but certainly not using the same tool, certainly not using primary decompositions and others which are primarily designed, Grosvenor basis and primary decompositions primarily designed to deal with polynomial equations, not inequalities.
Hello, may I ask?
Yeah, go ahead.
Yes, please.
Yeah, it looks like we are very successful in recovering physics laws, but I'm wondering what would be the problem to do biological laws.
Yeah, no, absolutely. That's a great question. So we started off with physics just as the natural sort of evolution of the systems we were looking at before. There has been some work in developing explanatory models for biological systems. The ones that we've run into when we were looking around for sort of alternate approaches typically tend to assume some functional form and assume some data on that functional form of the explanatory model. And so what they end up doing is some version of a traditional regression. I think so there's nothing, as long as you can encode theories in terms of polynomials, there's nothing stopping us from doing that. We just haven't looked at it yet. The sort of other bottleneck when it comes to, say, evolutionary biology is that you do have a lot of differential equations there, which, as mentioned, we're still working on sort of extending this framework to that context.
If I can add,
Because
again,
there is
Sanjeev
some
here from IBM, if I can add a quick comment, especially when you look at chemistry and many biology problems, there's a rates come in, the rate is important, the rate of change of something. And then that's a derivative, and then we can't really deal with that, except in very narrow cases, we can't deal with general derivatives and differential equations. But otherwise, yes, Karan said if it can be encoded in the same way, we can use the same tricks. The question is, can they be without getting into differential equations?
Yeah, I'm wondering because there is a known problem for mathematicians to communicate with biologists and even medical doctors, even worse. And the question is if the framework that you describe can ease that difficulty.
Yeah, absolutely. So I think that part of the reason we want to share and talk about this work is because while we have this system, there are of course many possible different domains that one could apply such systems to, and not just this work, right? Christina's AI Descartes work, Ryan's AI Hilbert work, and so part of this is also an open question to the audience of like, are there applications in your own work that you can see potential for using this kind of thing? Because we would love to hear more and to work with more people in the implementation side of these systems.
Very exciting. Thank you.
All right, thank you. Any last questions or comments?
Yeah, I have a question. So first, thank you for the talk. I think this work is really great, and it's very impressive that you can reconstruct some missing axiom. So my question is more about because in your work you assume that you can generate the kind of the theorem, so the hypothesis, the correct one.
Yes.
So then, but what happens if you suppose you remove one axiom, right, and then you generate an equation that simulate more the noise or is not the correct one, and then you try to abduce the missing axiom, and what happened in that case? You will just find a pair that is consistent, or did you, if you thought about this?
Yeah, no, that's a great question, and yeah, no, thank you for that. So we've played around to some degree with noisy versions of the phenomena, since of course with the symbolic regression or traditional data-driven approaches, you could get polynomials or phenomena that have this exact same monomials, but with coefficients perturbed. What we found is that there's certain kinds of perturbations that we can capture. Like for example, let's go back to this Kepler system. Yeah, great. So over here, like we see that, for example, in the first axiom, which let's say for now we don't have the second axiom, it'll make this explanation a little easier. If we just have this first axiom, D1 and D2 are added together and squared, and so you're gonna end up with some monomials of form D1 squared, 2 D1 D2 D2 squared. So if the polynomial that you're trying to fit to, or the perturbed axiom system, is perturbed in such a way that you're close enough to that same sort of ratio of coefficients between D1 squared, D1 D2 D2 squared, where it's roughly 1 to 1, then yes, you can recover perturbed versions of this first axiom if it were missing. But for more general perturbations, the system wouldn't be able to, it would struggle. It wouldn't be able to recover the right axiom. And so in that case, it would just sort of suggest appending Q to your axiom list, which is a bottleneck that we're trying to figure out how to address. Like one way one could do this is sort of clean up the noise a little bit in your perturbed polynomial Q. Let's say your noise is some real coefficients. Of course, in your axiom system, everything is rational or integer coefficients. We can just say rational for now. Then one idea that one could do is take all your coefficients and do a continued fraction approximation to get some rational approximation of your perturbed phenomenon, and then fit to that. When there's not too much noise involved, then that does work out. Again, with increasing amounts of noise, your approximation is poorer, and so then again, it depends on how much noise there is. But that's certainly something we are trying to work on right now.
So if you don't mind my just jumping in and
Please,
giving
go
a
ahead.
quick summary here. The point is that we have tried, it's a great question because it's a very natural question. What happens when you have noisy data? We have not succeeded in a true sense, in the sense that we're starting to get some understanding. I mean, ideally, what you would say is that if you look at a polynomial that fits the data and you're thinking of a perturbation, what could a perturbation be? Any arbitrary monomial, which, in the same degree or something, can get added with a small coefficient. That makes things very complicated. So What you have not done is go to the full extent of taking noisy data, fitting something. We just started with the intermediate question. What if we take the correct consequence and perturb that and then try to go backwards? What can we say there? And as Karan said, even there things are a little challenging, especially using the tools we're using. If you take the correct consequence, makes certain types of perturbations, as he explained, if the D1 and D2 you perturb things, but the D1 and D2 have the same ratio in the perturbation, then we can get back closely related axioms. So what I'm getting at is that small perturbations in the axiom system can lead to large perturbations in the consequence and vice versa because of the specific way we're doing things. We remember we're multiplying each of these axioms by a polynomial. And these polynomials, you get polynomial multipliers. So you can imagine if you perturb an axiom and then the multiplier gets multiplied with the perturbation and then carries through the whole. So you get, it becomes pretty complicated using this particular framework. So we don't have yet a good answer to the case of noise.
And because also you could have the system itself maybe is not powerful enough to produce the right theorem, right? So in that case, it's not really noise. It's more like the whole equation is wrong, right? But yeah, so from what I get from your answer is that up to a certain point, you can still recover something that makes sense. But then, of course, if the system created something very strange, then you cannot. But
that's one,
my follow-up.
And to be fair, this needs a lot more exploration. We have done some limited exploration to deal with noise. We do not have a comprehensive answer.
Yeah. But my follow-up question is that suppose you generate an hypothesis that is perturbated, right? So then you can still recover some kind of good enough axiom, missing axiom. So, but then maybe you can use this good enough axiom to do another round. So have you tried that? Because maybe this good enough axiom, then it will help to generate a less noisy hypothesis. And then you can do this in a loop. And maybe until you converge to the right one. Have you tried something like this?
No.
Okay.
Yeah, we
have
haven't
not.
tried something like that, but that's an interesting idea, certainly. I'd be curious in the original AI Hilbert work, and I think also in your work, Christina, I'm curious about how sensitive the sort of search process is or to noise in the axioms in the same way, because I think to achieve that kind of convergence, I think it would be interesting to play with both systems and see if we perturb certain axioms, what are the kinds of equations that we discover. If those perturbations are sort of small enough, then maybe this idea would be certainly worth trying it out. I think that's fascinating.
But as a general point, it's weird. We don't have the answers. That's a great idea, Krishna. And as a general point, these algebraic systems, as Karan mentioned earlier, because they try to come up with exact things, we don't have the right. Maybe these are not the perfect tools to come up with. You have some. So when you do it manually, you say, oh, I have a Taylor series approximation. I have these small terms, and you multiply something else. You always keep in your mind that there are these lower order terms which you can discard, and that we don't have a sort of a something inbuilt in our system to keep track of the lower order terms which you can discard whenever you feel like. So that would be something useful to have.
Yeah. And again, this could even amplify the error. We don't know, right? Could converge to the right one or could amplify the noise. So, but yeah, thank you.
Thank you for the question.
All right, any questions or comments? All right, seems not. Yeah, okay. Thank you again, Karan, for a nice talk, and also thanks to the team for coming. So I think we started the academic year with the project, and we are ending it with the same. And so maybe we'll continue the same series in the academic year. But for now, this is the last seminar for the academic year, and we'll all see you in October or so. Yeah, so maybe again with Karan for further work. All right, thank you all, and have a nice summer, and see you soon. Yeah, bye-bye.
Thank you.
Bye.